Welcome to the overview talk of the SympTEMIST shared task. My name is Martin Krallinger. I'm head of the Natural Language Processing for Biomedical Information Analysis unit at the Barcelona Supercomputing Center. And this talk is part of the overview talks of the BioCreative session at the EMEA workshop, EMEA Conference 2023. This is a joint work done with my colleagues at the BC, mainly Salvador Lima Lopez, the main responsible of organizing the track, Luis Gasco, Eulalia Faré, and myself, with some help of Jan Rodriguez. So basically, why did we organize a shared task related to a clinical NLP in Spanish? So obviously there's a big need to promote the generation of resources for clinical NLP applications in English, but also for other languages, in particular Spanish. So Spanish is a language spoken in 20 countries as official language worldwide, and it's also widely spoken by people unofficially in the US, Andorra and Belize. Overall, there are around 490 million native speakers worldwide, and all of these speakers could be regarded somehow also as potential patients. Just in the US, there's an estimation of around 42 million native speakers of Spanish as well. So there's a worldwide community in terms of patients related to content or to data in Spanish. But there's also a very active research community working on clinical NLP in Spanish, as can be seen from participation in past shared tasks working on data in Spanish. So there were shared tasks on clinical NLP in Spanish with participation basically at a global scale. Spanish is also a language which has quite well established resources in terms of terminologies, ontologies and lexical resources. So after English it's the language with the highest number of lexical entries, for instance in UMLS. And there are also terminologies for Spanish, for instance in SNOMED-CT, there's a Spanish version of ICD-10, of the human phenotype ontology and other terminological resources related to health-related data. There is a need also to actually go beyond monolingual clinical NLP applications. This is a current trend also in the general domain NLP field. So basically the idea also on having this task in Spanish and also generating multilingual subtrack, as you will see later on, has to do with the need to generate more multilingual resources for health-related data. So why did we focus on extraction of symptoms and signs in clinical data? Basically, signs and symptoms can be considered as a quite complex type of clinical concept, and it requires quite deep understanding of the medical field, the medical specialty, and also the clinical language. And it is also quite time-consuming to actually annotate and generate these kind of annotations or data sets. Despite this challenge, one needs to consider that it's a high-impact clinical entity or concept type. It's key for features in terms of predictive modeling of diseases. It's very important for differential diagnosis of complex diseases and emerging diseases. Also for the early detection of diseases, understanding of symptoms and signs is key. For the selection of appropriate treatments and therapies, the consideration of clinical symptoms and signs are very important, and it can be also used to actually differentiate, classify or group patients in terms of aspects related to the severity of diseases, progression, or to stratify patients according to some subtypes of a particular disease. So this is a key type of concept for many clinical application scenarios. I just pointed out a few of them. And there is a clear need to improve, to foster and generate resources for automatic extraction of symptoms from unstructured clinical data, from clinical content, from electronic health records, and also for clinical case reports. So where can you find symptoms, or from which kind of content can you actually extract symptoms? Symptoms can be extracted not only from clinical records, but also from literature, particular clinical case reports, also from clinical trials, from the web, from social media, patient-reported outcomes, patient forum, from patent theses, from questionnaires, so from really a wide diversity of types of content. We focus in this case more on clinical case reports and their application later on also for clinical reports. But there's also a need to foster and extract this kind of information from other kind of sources. Just to mention that the data we used for the SympTEMIST task was the same in terms of the clinical case report documents as has been used in the past. There were 3 shared tasks which shared the type of data set, this data set of 1,000 clinical case reports. For in this case, for the detection of disease mentions, which was the SympTEMIST shared task, the detection of clinical procedures, the MedPartner task, and also the detection of basically medications, drugs, chemical compounds, genes, and proteins, also from this particular subset of case reports which we are going to use for the SympTEMIST shared task. If you want to see more like global or integrated view on all these different annotation layers, you can see an example case of this data set used for the SympTEMIST shared task. So basically, same content, the same documents were annotated also for diseases, which can be seen in red in this example case, enfermedad in Spanish, symptoms, which is in blue, or procedures, which you can see in yellow. So if you go back to the SympTEMIST shared task, it was structured into 3 different subtracks. The first subtract was related to the detection of symptom sign clinical finding mentions in the text itself, so detect the exact offsets of all of the mentions of symptoms in the collection of clinical case reports. The second subtract was related to given a clinical symptom. Teams had to map or normalize, basically do an entity linking of these mentions to controlled vocabularies, and in this case we focused on mapping to SNOMED-CT, which has a very good coverage on signs and symptoms, basically to map and provide the SNOMED-CT concept identifier given a particular symptom. We also included a third shared task, subtract, more exploratory kind of setting, where we provided translated versions of symptoms which had been matched to also translated versions of the clinical case reports, and teams had to submit or provide, given a mention for instance in English, or a mention for instance in Italian, their corresponding SNOMED-CT identifier. So what kind of data did we provide as a gold standard, or training data, and also a subset for the testing or test evaluation for symptom detection? So there's a SympTEMIST gold standard data set consisted in total in the collection of 1,000 clinical case reports in Spanish, covering a broad variety of different medical specialties and disciplines: cardiology, ophthalmology, urology, oncology, mental health, rheumatology. So it had a quite big coverage on different kinds of clinical case reports. This collection of 1,000 case reports was divided into a training and test set for the mention recognition track. 750 documents were used as training set, and 250 documents were used as a test set. In total, if you join both collections, this data set had a total of over 12,000 manually annotated mentions with SympTEMIST. Here you can see also in this slide the distribution among training and test set. A subset of these mentions were also mapped or normalized by clinicians, by clinical experts to SNOMED-CT concept identifiers, and you will see this a little in more detail later on. The inter-annotator agreement was measured as pairwise percentage agreement between clinicians, the clinical experts for the mention annotation, and it had an inter-annotator agreement score of 79.1. So annotating these kind of mentions is quite challenging, even for clinicians, one has to say. We do release the dataset freely. It's available at Zenodo at the link you can see on this slide. So for the annotation process, we also prepared quite detailed annotation guidelines with rules followed by the clinical experts to label and these kind of mentions. The annotation guidelines had positive rules, negative rules, so what had to be labeled, what didn't have to be labeled, also more like general rules, and rules also for doing this mapping and normalization of mentions to SNOMED-CT concept identifiers. These guidelines are also available to the public, and can be downloaded at the Zenodo link you can see here. The mentions were annotated in terms of the exact character offsets. So here you can see in the slide the running text in blue, and basically the labels which were annotated by the clinical experts, and below you could see the corresponding character offsets, so where this mention starts and ends in these particular documents. So these standoff annotations were provided as in two formats, and .n, and the PRAT format, and also a TSV. And basically teams had to predict these kind of exact matches of these offsets for the mention recognition subtract. So for the normalization or entity linking, basically we use a subset of these 1,000 clinical case reports, namely 600 clinical case reports divided into a training set of 350 and a test set of 250 case reports. So basically for each of these data sets, given the mentions of these clinical symptoms, teams had to provide the corresponding SNOMED-CT concept identifier. We only used mentions of symptoms which had been manually mapped to a single SNOMED-CT concept identifier, and for this task we actually disregarded mentions of nested or multiple entities. For doing or for assisting the manual annotation process, we also built a tool called Krallinger, which were used by clinical experts to be more consistent and efficient in the manual annotation process. So going to the corpus or dataset itself, so you can see here an example case in Spanish, where basically the patient is described, a patient of 58 years of certain origin and so on, basically is described there, and then some symptoms are actually associated or described related to the patient itself. So these symptoms were manually annotated. Some of them are quite straightforward and can be even single token mentions. But if you look at symptoms across the corpus, some of them are quite complex and narrative and descriptive. So even for humans to annotate these type of entities is quite challenging, and obviously also for automated systems. And some of these symptom mentions actually are also relevant in terms of the annotation of clinical phenotypes. In this example, actually, it describes a newborn child, and also basically some more like morphological phenotype characteristics related to this particular patient. As additional resources for participating teams, we actually had a look at SnoMedCT. So SnoMedCT does have a quite large collection of concepts, but only a subset of them are relevant for annotating disease symptoms, signs, and findings. And to make this subset selection a little more straightforward for the participants, we generated a gazetteer of mentions of concepts from SnoMedCT, which are actually relevant for normalization and for harmonization of symptoms for this particular shared task. In addition, we had a third subtrack, as I mentioned, more related to normalization of signs and symptoms for other languages than Spanish. So basically for English, for Dutch, French, Italian, Portuguese. We generated also additional data set for other languages such as Swedish and Romanian and Catalan. And here you can see a little how this data set looked like. So given the Spanish gold standard, we generated a translated version of the clinical case report. We also generated a translated version of the symptom mentions, which was done basically mapped using a specific, let's call it a lexical transfer approach to assign the corresponding symptom mentions in the translated data sets. So looking at the participation at the SympTEMIST shared task, we had in total 25 teams registered from 19 countries. Out of these teams, a total of 11 participated in at least one of the subtracks. 10 of them participated in the first subtrack on clinical symptom mention recognition with a total of 42 submissions. In case of the entity linking, we had 7 teams with 23 submissions. And then for the multilingual subtrack, where we have to remember that we had submissions for each of the languages basically released. So for English, for Italian, and so on, we had 2 teams with 23 submissions for these various languages. One has to mention that for the entity linking multilingual shared task, we didn't have, participants didn't have that much time. So maybe for the future, we would allow more time also for training and testing of participating systems. In the table, you can see the different teams. So they included teams from the University of Aveiro in Portugal, for Bogazici University in Turkey, for Yitzo, a commercial participant in Spain, from Bulgaria, Sofia University, from Germany, the Hasso-Plattner Institute. We also had participants from other universities in Spain, for instance, the University of Malaga or the Carlos III University, but also from Canada, from Italy and Greece. So overall, the participation was quite global, one has to say. In case of the obtained results, the top scoring teams actually reached quite competitive results. So in case of the exact, basically exact mention detection of the offsets, the best scoring team could reach a balanced F-score of 0.74. So it's quite close actually to the results being achieved by the manual annotation process, with a precision of 0.8, very high, and a recall of 0.69. In general, one can say that the recall results were slightly lower than the precision results. So this is basically also due to these very long mentions of symptoms, more descriptive ones, which are a little more difficult to get right in terms of exact character offsets. If you look at the second part of this table, or the partial overlaps, obviously the results look a little better, and the best teams could actually reach F-scores of around 0.86. As highlight, all teams use basically some sort of transformer-based architecture. Many of them also explore the use of some common model architecture like Roberta. Top scoring teams also explored some sort of ensemble model techniques and data augmentation. So overall, one has to say these results are very competitive and close to the human annotation quality. So I'm not going into lots of technical details of the top scoring team. So the top scoring team was for the mention recognition from the University of Malaga, and it used some sort of combination of different pre-trained transformer-based models. And there's a publication also, you can see the reference on the slide, detailing more like the settings and the approaches used by this team. For the entity linking or mapping to SNOMED CT, the results in terms of accuracy, the best team could reach an accuracy of 0.6. If you look at the basically highlights or what kind of things should be outlined by participating teams, so they use some supervised but also unsupervised techniques. One could see also the usage and application of semantic search and textual similarity across multiple of the participating teams. And there are also teams more related to the usage of question answering approaches for the normalization problem, or also the use of different approaches which can be related to lookup and terminological database exploration. So the top scoring team, as I mentioned, had a F1 score of 0.6. It was from the Hasso-Plattner Institute. Here you can see a summary of the methodological approaches which was followed by this team. And there's also a reference and some GitHub link related to the X-Men resource generated and released by the participation of the Hasso-Plattner Institute. So for the third subtrack, the multilingual normalization, this is an experimental track. So we generated some translated versions of the symptoms and asked teams to normalize or map them to the corresponding SNOMED CT identifiers. So here we only had two teams, the PICO's lab and the University of Aveiro. And you could see the accuracy results for instance, for the University of Aveiro team for English was of 0.72, and for Italian of 0.67, so quite good. And you can see also the results for other languages. So both teams used some sort of re-ranking based approach, and they incorporated also some additional, let's say, pipelines exploring machine translation strategies. So to summarize and to conclude what we learned or what could be taken as a take-home message from the SympTEMIST shared task. So we generated multilingual resources and settings through this task beyond only a monolingual approach using Spanish. So it's an initial exploratory task, so it needs some, let's say, additional analysis and exploration. Definitely would need to expand the data set and generate proper gold standard annotated data collection for all of these languages, with clinical sites collaborating for generating these multilingual data sets. We also generated obviously a large collection, a new data set, corpus, guidelines and lexical resources for the detection of symptoms and signs in clinical data in Spanish. Overall, the results are really very good. They're close to human annotation performance. There is still some room for improvement. And there's also obviously a need to annotate more data and more case reports, to include also clinical records, not only case reports themselves, to increase coverage across different specialities, and also to try to improve slightly also the annotation consistencies. So finally also we would like to see how these results can be actually used in practice, how they can be integrated into clinical NLP pipelines, and to align to clinical use cases and applications, clinical data mining and predictive modeling. So just to highlight also, this data set was used also to generate and train a system to generate pre-annotations of clinical records, so hospital records, different types of clinical records, including discharge summaries, clinical notes, and other kind of clinical content types. And it had been the base of semantic annotation of symptoms for the CARMEN-1 dataset, which has been released just like as a brief, a couple of days ago at the Physionet platform. And here you can see the link. So this is also, let's say, a success that this kind of open data sets based on case reports can be used as a surrogate for clinical records and peer annotations. So all of the resources we generated for this shared task are open, they're freely accessible, and we really encourage feedback and usage of these tools and resources. I also want to thank the members of the team of the NLP for Biomedical Information Analysis at the BC. So most of the work was done by Salvador Lima, and also Luis Gasco and Jan collaborated more on the technical development of these resources, while Eulalia Farré collaborated and supervised the annotation process done by clinical experts to generate this highly valuable dataset in corpus.